Okay, thanks, William. So this is joint work with Mitali Bhavna, currently at MIT, and my advisor Pravesh, who is now at Princeton. Okay, let's get started. So the problem today we'll be looking at is finding a large independent set in a graph. So this is probably one of the most fundamental questions in computer science. So first of all, we know that it's NP hard to find the maximum independent set in a graph. But we actually know something much stronger. We know that the independent set problem is NP hard to approximate. So this is a precise statement. Given a graph that contains an n over polylog n size independent set, so a pretty large one, it's NP hard to find an independent set of size n to the little o of 1. So there's a huge gap between what's guaranteed and what we can find here. In particular, it's hard to approximate independent set within a factor that's better than n to the 1 minus little o of 1. Okay, what about the best known algorithm? So given the same guarantee that you have an independent set of n size n to the polylog n, the current best known algorithm can only get log squared n. This is by Hsieh in 2004, and it's the best known algorithm since then, so it's been like this for 20 years. So basically, this shows that it's hard to do anything. We have very strong hardness results, and the best known algorithm is pretty bad. But here's the catch. This is only in a very low completeness regime. So low completeness means that we are guaranteed the graph contains only an independent set of size n over polylog n. So in particular, we can ask, what about the high completeness regime? What if we're guaranteed a larger independent set in the graph? So here, when I say high completeness, that just means that we have the graph contains an independent set of size linear omega is n. So we have a much stronger guarantee. Can we do better? Here's a trivial algorithm. Suppose the guarantee is larger than half plus epsilon times n, so it's larger than half of the graph. Then there's an easy algorithm that gets 2 epsilon n. This is just by the simple two-factor approximation for vertex cover. So it's a very simple exercise. You can see this by noting that the complement of an independent set is a vertex cover. But what about below half? If you're only guaranteed an independent set below half times n. Well, unfortunately, in this case, we have hardness result. Assuming the unique games conjecture, it's hard to find any linear sized independent set, even if you're given a graph that contains half minus epsilon times n. And the best known algorithm in this case gets n to the 1 minus O of epsilon.
Can I ask a question? Sorry, maybe I missed it at the beginning. The it's a two-parameter criterion. The first thing is the number that actually exists in the graph.
Correct.
And the second one is what you can achieve.
Yes.
Polynomial time. Is that what this?
Yes. So it's the completeness and soundness of hardness results. Yeah. So yeah, just to as a reminder, this parentheses means that, for example, given a half minus epsilon times n size independent set in a graph, it's hard to find any independent set of size epsilon n. Thanks, Danny. Okay, so before I go on, let me explain why we even care about the high completeness case. And among many reasons, one main reason is that it has a close connection to coloring 3-colorable graphs. So, simple observation, a 3-colorable graph always contains an n over 3 size independent set. So this is automatically in the high completeness regime. And this problem has been studied in a long line of work. This problem is basically, given a 3-colorable graph, you color the graph with as few colors as possible. And let me mention that all of these previous works, what they do is given the graph, they find a large independent set, as large as possible, and they color that with a single color because there are no edges between any independent set, so you can use one single color. And then they recurse. So remove the vertices and the recurse. And currently the best algorithm is able to find an n to the 1 minus roughly 0.2 size independent set. And then this automatically implies that you can color the graph with n to the 0.2 colors. This is actually a very recent, the best known algorithm is a very recent paper in stock this year. Okay, but what about hardness? We also have quite strong hardness result here. Assuming the unique games conjecture, but here we need a variant of the unique games conjecture that has perfect completeness. It's not too important. It's hard to find, again, hard to find any epsilon n size independent set. So basically, so far I've told you a lot of hardness results, and the conclusion is just that worst case graphs are very hard, and assuming these conjectures, the unique games conjecture, we cannot do anything. But we shouldn't stop here. We should ask, what other assumptions can we add to the graph so that the problem becomes easy to escape the worst case hardness? And in particular, this is basically the idea behind, for example, like smooth analysis or average case analysis. We're asking what are some minimal assumptions on the input we can add so that we get non-trivial algorithms. We escape the worst case hardness. One example that people have studied is random graphs, k-colorable random graphs. It was observed that in this case, the bottom eigenvectors of the adjacency matrix contain a lot of information about the color classes. So they're able to use the bottom eigenvectors to recover a k-coloring of a random k-colorable graph. And this idea of using the bottom eigenspace is not just restricted to random graphs. It can be extended to tangent k-coloring on two-sided expanders. So this means that both the second eigenvalue and the minimum magnitude of the minimum eigenvalue of the adjacency matrix is at most some small constant delta. So basically they use the same idea of using the bottom eigenspace, and people have come up with algorithms that either recover an almost k-coloring or at least find a large independent set in the graph.
Sorry, so what are the bottom eigenvalues? Are they like the smallest in magnitude eigenvalues?
So
the second eigenvalue?
the adjacent matrix, so lambda 1 must be 1, or the normalized adjacent matrix.
Right.
So lambda 1 must be 1,
yeah.
And then you sort the eigenvalues in decreasing order.
Yeah.
So there are going to be some negative ones.
Mm-hmm.
So the bottom eigenspace corresponds to the negative.
I see. So
eigenvalues. Yeah. Okay. Thanks. All right. Okay, but notice that. Thank you for the question. Because I'm gonna notice that all these techniques rely on the bottom eigenspace. So they actually only care about the minimum eigenvalue. The algorithm doesn't really care about lambda 2. So this is a little bit strange, because usually when we say expanders, we usually think about lambda 2, because the close connection between the second eigenvalue and edge expansion. So their assumption that lambda n is bounded is not exactly an assumption on expansion. So we can ask, what about if we only have upper bound on lambda 2 and not lambda n? And this is what we call one-sided expanders. Just as a quick reminder, the second eigenvalue being small is roughly equivalent to the graph having good edge expansion. And this is just by the famous Cheeger's inequality. So basically we're asking, suppose we have a graph that has good edge expansion. Can we do better? Can we do better than beat the worst case hardness? So unfortunately, another hardness result. We show that assuming the Unique Games Conjecture, it's hard to find any linear sized independent set in an almost 4-colorable graph, even when lambda 2 is below little o of 1.
So Tim,
Mm-hmm.
The other point is that you're like allowing graphs that have like an eigenvalue near -1.
So actually, for 3 colorable, like k-colorable graphs, wait, sorry, what's the question again?
But like the point is like now you're trying to like allow graphs that have like pretty negative eigenvalues.
Or like many negative eigenvalues.
But are they kind of like intuitively not so bad? Like if you have a really big negative eigenvalue, it's like you're like closer by infinite. So you should have a huge by infinite set anyway.
Yeah. So maybe you can think of it as has many eigenvalues at like -1/3 or something.
Okay.
Yeah. So the previous works they show that even if you have few negative eigenvalues, like the negative threshold range is small, you're able to get a good algorithm. So maybe you can think of it as the graph having many eigenvalues at below like -1/10, for example. Yeah. Does that clarify your question?
I'm just wondering like how that intuitively helped to assume that there's like no very negative eigenvalues.
I think basically if it's the idea that the eigenvectors have information to recover the coloring. So if the eigenspace has low dimension, then you can basically just enumerate over that space. Yeah. Okay. Okay. So here, okay, let me go back to this. So almost here just means that you can remove a small fraction of the vertices, so that the resulting graph is 4 colorable. And I'll let me mention that the previous works using bottom eigenspace, their algorithm can be extended to any k-colorable graph. So there's already a difference here between λ2 and λn, because their work can work for any k, but here even for 4 colorable it's hard. And I'll quickly show you the proof. The proof is quite easy. The reduction starts from this lemma by Benson and Gold. Given a graph, it's usually hard to distinguish between the following 2 cases. The first case is when the graph has 2 disjoint independent sets of size half minus epsilon n. This is equivalent to saying that the graph is almost bipartite or almost 2 colorable. The second case is when G has no independent set of size epsilon n. Okay, so we want to start from this harness, and then we want to reduce to a problem that get the harness result. What do we do? Given a graph, we'll just add a large bipartite graph in it. So we arbitrarily partition the vertices into 2 sets, and we just add edges. Add a dense expanding bipartite graph. So in the first case, because the original graph is almost 2 colorable, then when you add a bipartite graph, it becomes almost 4 colorable. This is just because the bipartite graph is 2 colorable, so you can use 4 colors. And then in the second case, the original graph has no large independent set. But then adding edges cannot increase the maximum independent set size. So that's the soundings. And finally, we need to check that the second eigenvalue is small. But this is also easy to see, because if the bipartite graph is dense enough, then the spectrum of the adjacency matrix is dominated by that bipartite graph. So the second eigenvalue is going to be little over 1. That's it, that's the reduction and the proof.
We put complete bipartite graph.
Maybe not complete, but like an expanding one, and dense enough.
Why not?
Well, if it's complete, then I think it's easy. But it cannot be too dense, because if you have the maximum degree d, then you can easily. Maybe it's possible to get.
I'm not wondering why it's easy. Like I'm wondering like what part of your reduction uses the fact that it's the bipartite graph you put down is not too dense.
Actually, you might be right. Maybe it's fine. It's fine to have a complete bipartite graph. I'll need to check. Yeah. Okay. But as long as it's dense enough that it dominates the spectrum, then this reduction works. Okay, so just so remember in the previous works, they're able to get an algorithm as long as lambda and or the negative eigenvalues are bounded. So basically, what this shows that in this reduction, the resulting graph must have many negative eigenvalues. Otherwise, their techniques should work for it. Okay, any other questions about this reduction? Okay, so I've told you a lot about hardness results. So finally, some algorithms. Our first result is that suppose we're given an almost 3-colorable graph, and suppose that the second eigenvalue is at most 10 to the negative 4, some fixed constant. And there is a polynomial time algorithm that finds an independent set of linear size. This is quite surprising because in comparison, the previous hardness result says that if you replace 3 by 4, then even if you assume a stronger assumption that lambda 2 is at most little of 1, it's usually hard to find any large independent set. But there seems to be a fundamental difference between 3 and 4. And to be honest, we don't know exactly why. We know exactly where this breaks down. I'll pause for a few seconds.
Oh, now you put the word regular in there?
Yes, I put the word regular, yes. Good catch. So we didn't really care too much about irregular graphs.
So the reduction from the previous slide makes regular graph?
Yeah, you can make it regular, yes.
If the original graph is regular, then it's going to be regular.
Okay, so we have a second result. So instead of assuming the graph is 3-colorable, suppose it contains an independent set of size half minus epsilon times n. Then here we only need the second eigenvalue to be not too close to 1. Suppose lambda 2 is upper bounded by 1 minus some constant times epsilon. Then there's a polynomial time algorithm that finds an independent set of size omega n. And this in particular immediately implies a corollary for almost 2-colorable graphs, because any almost 2-colorable graph must have an independent set of size close to n over 2. And notice that both of these theorems, they have assumptions on the second eigenvalue. So in particular, we're assuming that the graph is an edge expansion. We have a third result that replaces edge expansion with vertex expansion. But we also need an additional property that is we have a certificate of small size vertex expansion. So for this result, I won't go into detail in this talk, but I'll quickly come back to this at the end when I talk about open questions.
So for the positive result on the previous page, you need the almost coloring, like it's not enough to have an independent set of size near 1/3?
Yeah, that we don't have this. Good. Okay, so for the rest of the talk, I'll talk about 2 main ideas that go into our proof. The first is a clustering property of large independent sets in expansions. This says that there cannot be too many near disjoint large independent sets. Or in other words, any constant number of large independent sets must have large overlap. And I'll define the precise definitions later. The second idea is that the clustering property implies rounding algorithms. And right now, just as a high level, our algorithm relies on this idea of rounding using multiple samples from a pseudo distribution. Okay, so for the first one, the first result is purely combinatorics. So if you like combinatorics, then I hope you will enjoy this result. The second one is algorithmic, so it's using tools from sum of squares hierarchy. And for this talk, I won't have time to go into too many details of sum of squares. I don't really have time to define everything here, but I'll still quickly mention the high-level idea using sum of squares. Yes, thank you.
Are you, so you're not gonna prove the theorem about the three colorability result?
I'll prove the first part, and the second part I'll kind of skim over, and that these two combined imply that.
Okay.
Yeah.
So this is the main idea is the proof of the theorem you proved?
Yes.
Okay.
Okay, cool. Let me continue. So I'll first start with the second result, which is finding large independent sets in expanders that contain a half minus epsilon n size independent set. Okay, so let me first define what clustering of independent sets mean. Like, how do we define two distinct independent sets? Let's consider two independent sets x and y. They're represented by 0, 1 vectors, and they both have size half minus epsilon n. Then if these two are roughly random, then we should expect them to have intersection roughly 1/4 times n. Here's a mental picture to keep in mind. Two independent sets partition the graphs into 4 parts. For example, the 0, 1 part contains the vertices where xu equals 0 and yu equals 1. The second, so this 1, 1, is a part where the vertices have xu equals yu equals 1. So in particular, the intersection between x and y is exactly the size of this part 1, 1. And here you should also think of the edges in this 4 vertex graph as representing edges between the parts. So for example, we cannot have any edges between 1, 0 and 1, 1 because these are considered in the same independent set by x. Similarly for 0, 1 and 1, 1. Okay, so we're gonna define distinct to mean that the intersection is at most n over 4. Here's our lemma. So suppose the second eigenvalue is upper bounded by 1 minus constant times epsilon. Then for any 3 independent sets of size half minus epsilon times n, 2 of them must have intersection larger than n over 4. And we're actually going to prove that like close to half. In other words, this means that there cannot be 3 distinct large independent sets. When we define distinct to mean intersection at most n over 4. Okay, any questions about this statement? Yes, no?
So you could say something just using like counting, inclusion, exclusion type thing, right?
Say what about?
Like if you have 3, like by like a packing argument or something,
Right.
right? So this has to be the n over 4 is stronger than what the constant is better than what you would get if you just did like a counting argument because you use the additional assumption.
Yeah, just by the count.
Like if you didn't make an assumption on lambda 2, I think you could still have some. Like clearly, for instance, they can't. The intersection has to be non-zero, right?
Well, it might depend on epsilon, right? Because if epsilon's pretty large, then actually the counting argument wouldn't work. So if epsilon's like 1/4.
Yeah, but
I think no, you're right. Let's say epsilon is super tiny.
Okay.
Then in that case, you do get some like. Wait, actually, did you get 1 over 4?
It's like you get
Slightly less.
Yeah. So this, yeah.
I'm just wondering, can you give like an example of the lemma failing when lambda 2 is really close to 1?
Let me think. Maybe I can draw the graph, but good question. I'll get back to that later. Okay, like I think I can draw some graph that satisfies this. Okay.
Yeah, if you have lambda 2 equals 1, you could have only n to the n over 3 overlap. If you like split your graph into 6 parts, and then like
Yeah.
anyway, sorry.
Do you need it to be close to half or just bigger than n over 4?
We just need it to be bigger than n over 4 for our algorithm to work.
So for the counting thing, I guess you're right. Like you get n over 4 minus that n like 1/4 minus order epsilon or something. So
Yeah.
you're probably winning from you're getting something better.
Yeah, thanks so much for the questions. Here's a high-level proof idea. So we first start out with two independent sets, and we say that suppose they're distinct, meaning that they have intersection at most n over 4. Then with the expansion assumption, it implies that the graph has some specific parquet structure. So this is a very high-level proof idea, and then once we have this, we'll go to three independent sets and get some contradiction. Okay, I'll start with the simple claim. So here, W of 0, 0 means the weight of the set. So it's the size of the set divided by n. And remember that two independent sets partition the graph into four parts. The first claim is very easy. It says the weight of 0, 0 is at most the weight of 1, 1 plus 2 epsilon. And this is just by the fact that both independent sets are large. So 0, 1, 1, 1 and then 1, 0, 1, 1 are both at most half minus epsilon. So when you add them together, you get 0, 1, 1, 0, and then 2 times 1, 1 is at least 1 minus 2 epsilon. But we also know that all of them sum up to 1. So this means that 0, 0 minus 1, 1 is at most 2 epsilon, and we're done. So it's basically a simple claim that 0, 0 must be roughly 1, 1, or at most 1, 1. Now the second claim uses the expansion. So we're going to apply the expansion on this set 0, 0, 1, 1. And the statement is that 1 minus lambda 2, and notice that 1 minus lambda 2 is the second eigenvalue of the Laplacian. So it governs the number of edges that leaves the set. So 1 minus lambda 2 times the weight of 0, 0, and 1, 1 times the complement is at most 0, 0 minus 1, 1. Okay, and again, the proof is quite simple. So we apply the expansion to this set. So we have that, okay, the red edges are the outgoing edges of this set. So here it's denoted by E. The edges between 0, 0 and 0, 1 plus 0, 0 and 1, 0, these are the outgoing edges of the set. It's at least the second eigenvalue of the Laplacian times the weight times the complement. Okay, now we use, to answer your question, we use regularity here. So in particular, we have that the weight of 0, 0, or the weight of any vertex set equals the weight of the edges, incident edges of that set. So here 0, 0 has 4 incident edges, like this. 1, 1 only has the edges between 0, 0 and 1, 1. So when you subtract these together, you basically get that result. You're combining all these three inequalities. All right, so now we want to combine these two claims to get our result. So by rearranging, we get that the weight of 0, 0, 1, 1 times the complement is at most 2 epsilon divided by 1 minus lambda 2. And when lambda 2 is at most 1 minus some constant, let's say 20 times epsilon, then we get that this is at most 0.1. So notice that on the left-hand side is a quadratic polynomial. It's a number times 1 minus that number. So if this is at most is very small, it must mean two things: that this number is very big or very small. So either it is below 0.1 or at least 0.9. So here we have two cases. In the first case, 0, 0, 1, 1 is very small, so 1, 0 and 0, 1 is very big. So the graph actually looks like this. The four partitions are very imbalanced. And the second case is when 0, 0, and 1, 1 is at least 0.9.
Wait, sorry, what is W0011? Is that the
Yeah, thanks for the question. It's just weight of 0 plus the weight of 1, 1.
Oh, okay.
Yeah. Okay. But notice that in the second case we're done, because 1, 1 is the intersection between the two independent sets. So if it's larger, then we're done.
Wait, if it's just the sum, then couldn't like 0, 0 be really big? So
Yeah, good question. But we also have the previous first claim.
Okay.
Yep. But yeah, I was trying to hide that under. Okay. Okay, so we only need to work in the case, but in the first case. But notice that in this case, this graph has a very specific bipartite structure. In particular, if you remove the small 0, 0, and 1, 1, this graph is bipartite. So this shows the claim that, the two distinct independent sets and expansion imply this specific bipartite structure. Okay, now we want to finish the lemma, so we'll go to 3 independent sets, and then assume, but for contradiction, that each pair is in the first case. Okay, so we want to say that this cannot happen. So I have that the first 2 independent sets satisfies this inequality, and similarly the first and third, and the second and third. So why is this a contradiction? So we can sum them up, and the right hand side is 0.3. And the left hand side I claim must be at least 1. And this is just because when, the star means that you can put anything there. So why is the left hand side at least 1? It's because for any 0, 1 string of length 3, it must have either 2 zeros or 2 ones. So everything is covered on the left hand side. So we get a contradiction, and then we're done. Basically, we say that we show that one pair must have 0, 0, 1, 1 at least 0.9, the second case. In which case, the intersection must be at least 0.45. So it's larger than 1 over 4.
And the 0.45 is coming ultimately from the choice of C, right?
Yeah, choice of
If
C.
you make C really big, then you
Yes,
make that.
yes. So that's why I said earlier that we can actually prove it's close to half.
Yeah.
So where did you apply expansion here again? Sorry.
Expansion is from the second plane, and then by rearranging the second plane and combining these two planes, you get this. You get this inequality.
I see.
Yeah. Okay. So that's the proof. Any questions? Okay, that's proof. Okay, so this is what we've seen. Any 3 independent sets must have, 2 of them must have large intersection. Now I'm going to tell you how this is implying an algorithm. And in particular, why do we need n over 4 to be the threshold? Okay, so let's, for simplicity, assume that now we have just 2 independent sets with intersection larger than 1 over 4 plus some constant delta. Then we'll show that we can find an independent set of size delta times n, omega of delta times n. And here's a high-level proof. So I won't go into any sum of squares details. So let's just think of it as a distribution, that we have a distribution over independent sets. This is represented by 0, 1 vectors. Now we define Pu to be the probability that xu equals 1. So the probability that a vertex u is included in an independent set when you sample from mu. And here's a simple observation. The vertices such that Pu is larger than 1/2 must be an independent set. The simple exercise, you can see that for any edge, and look at the endpoints, their marginal probability cannot be both larger than half. Pretty simple exercise that you can do. And now we want to consider 2 samples from mu. So mu times 2 just means 2 independent samples. And then we look at the expectation over x and y sample independently, their intersection. And W11 can write it out as the expectation over U, XU, YU. And then this is the expectation of PU squared. So if we have this is at least 1/4 plus delta, then we know that at least delta omega of delta fraction over these have PU larger than 1/2. And that's it, we're done. Okay, so this is the end of the independent set result. Any questions?
So this is where the SOS stuff is?
Yes, this is where SOS stuff is. So for people who are more familiar with sum of squares, we need to replace distribution by a pseudo distribution.
It's only degree 2 though, so I mean, is it just like some basic SCP thing?
Yeah, okay, the catch is we also don't have this exactly. We don't have that exactly. Remember that the lemma is that for 3 independent sets, 2 of them have large intersection. So it's not as easy as just replacing mu with mu tilde. It's not exactly the same. So there's some additional work to be done. But this is the high level idea.
And where does the proof fail if you get a 4-colorable graph?
Oh, I haven't got to the 3-colorable proof yet.
Oh, okay.
But we'll see.
Okay.
Yeah. Okay. The next part is 3-colorable explain. Yeah. Okay. 18 minutes. Okay. So again, for 3 colorings, we need to define what do we mean by distinct, or what do we mean by agreement. So let's look at these 2 graphs. These are 3 colored. And let's say the vertices are labeled, so we cannot permute the vertices. These 2 colors should be the same because we can permute the colors. Even though these 2 colorings color the vertices differently, we should consider them to be the same color, same 3 color. So this motivates the definition of agreement between 2 coloring to be according to some permutation pi of in S3. So the agreement of x and y according to pi is just a fraction of vertices where xi equals pi yi. And then the natural definition of agreement is just the max over the permutation. All right. And so I'll skip over this. Just an example. These 2 different colorings, they have agreement half. I'll skip this part. So for 2 colorings, they're represented by vectors in 1, 2, and 3. They partition the graph into 9 partitions. This is very similar to the previous case for independent sets. For example, the 1, 1 part is the vertices that are labeled 1 by both x and y. And notice that this graph is actually the graph triangle tensor 2. Okay, and these, I've highlighted a few triangles. There are 3 triangles that are highlighted. These exactly correspond to the permutation, the agreement according to permutation. So for example, the green one is an identity permutation. So for 2 roughly random colorings, we should expect the agreement to be roughly 1/3. Okay, so we're going to define distinct to mean agreement at most half. So it's stronger than 1/3. And we will see later why we need half in the end. So here's a lemma. If the second eigenvalue is at most 10 to the negative 4, then any 3 colorings, so here we need additional assumption that no color class is size n/2. Because in this case we're already done. We already have an algorithm, the trivial algorithm. So for any 3 colorings, not too large, 2 of them must have agreement more than half. In other words, we cannot have 3 distinct 3 colorings. And the proof idea is basically the same as before. We want to show that, let's consider 2 distinct colorings for now. Suppose they're distinct and they have expansion, the graph have expansion. Then it implies that this graph has some specific bipartite structure. Basically roughly the same idea as before. Okay, so let me prove this claim. I'm going to define S pi to be the set I and pi I, where I ranges from 1 to 3. So each S pi in this graph corresponds to one triangle that looks like this. And then the agreement of x and y, according to pi, is exactly the weight of S pi. Okay. So observe that, for example, in this graph, this 9-vertex graph can be partitioned into 3 triangles. And these triangles correspond to permutations of the same signs. So look at, this is, the green one is 1, 1, 2, 2, and 3, 3. Similarly, the red and blue ones are both permutations of positive sign. And there are 2 different partitions because we have 6 permutations. 3 of them are plus and 0 of them are minus. So there are 2 ways to partition this 9-vertex graph. The other 3 triangles are not drawn out in this picture. Okay, and then now we're going to apply the expansion on S pi. So the edges between S pi and S pi complement is at least the second eigenvalue of the Laplacian times the weight of S pi times the complement. And then now we just sum everything up. So okay, we get this inequality. It's not immediately obvious that you get 1 on the left-hand side, but one can see this by just staring at the graph long enough. You can see that each edge is counted exactly twice. And because the sum of all edges is half, so we get 1 on the left-hand side. I won't explain this like in full detail, but this is just by staring at this graph long enough, you'll see it. And then for the right-hand side, the sum of WS pi, again, we can see that each vertex is counted twice when you sum up the permutations. So you get 2. And then we get a sum of squared WS pi. By the rearranging, we get that the sum of squares is at least 2 minus 1 over 1 minus lambda 2. And where lambda 2 is at most epsilon. I apologize, this epsilon is different from the previous epsilon. Let's think of it as like 10 to the negative 4. So when lambda 2 is very, very small, then the sum of squared weights is at least 1 minus epsilon. So in particular, we already see that agreement cannot be 1/3. Because if agreement is 1/3, then every S pi has weight at most 1/3. Then we have 6 permutations, so 6 times 1/3 squared is 6 over 9, which it cannot be larger than 1 minus epsilon. Okay, so what do we have now? We have 6 triangles. We know that 3 of them must sum up to 1. We also know that their squares sum up to at least 1 minus epsilon. So how can this happen? Well, one example is this. You have half, half, 0, and half, half, 0. The first 3 sum up to 1, the second 3 sum up to 1, and then their squares sum up to also 1. So we're going to show that this is the extreme case. So we will show that either one of them is at least half plus delta, or 2 of them must be close to 0. The first case, because each of these, the maximum of these 6 numbers is the agreement. So in the first case, we have agreement larger than half plus delta, and then we're done. So let's assume that we're in the second case, but 2 of them must be close to 0. And what does that mean? It means that we can basically zero out 2 triangles in this 9-vertex graph. And basically, so this is an example where we delete 2 triangles. So we're left with 4 vertices, and the 4 vertices are bipartite. So again, this is the claim that 2 distinct colorings plus expansion imply that the graph is almost bipartite. So now, again, we go to 3 colorings. I won't have time to go through this part, but basically, by the previous claim, we can show a contradiction. So unfortunately, I only have 10 minutes. I'll skip this. And this slide is about why having agreement larger than half gives you an algorithm. I think for the time being, I also skip this part. This is basically the very similar calculation as the independent set case, but instead of independent sets, we have coloring. So we need to look at like the well, the end goal is to show that there are at least delta fraction vertices satisfy this inequality. That the max over the three colors, the probability that xu is assigned to some sigma is larger than half. And again, this is by the same observation that all vertices with this larger than half, with a specific sigma, that with probability larger than half must form an independent set. So sorry, I don't have time to go through this, but I want to get to some open questions. Okay. So what if we don't have any assumption on the expansion? What if it's the worst case graph? So we know some worst case hardness that we cannot beat. The best known algorithm is right now is n to the 1 minus O epsilon. So the obvious question is, can we beat this current best known algorithm? And one natural idea is to do graph decomposition. We can decompose the graph into expanders and then solve each piece. And this is a strategy that Jason knows very well, and I guess for unique games, this is what they do to get the sub-exponential time algorithm for unique games. So basically, this has been done before. People first study the case when the graph is an expander, and then for worst case graphs, they decompose and then solve each piece. But for independent set, here's a problem. How do we piece them back together? So suppose you have a decomposition. Each of each piece is an expander, so you can zoom in and then solve each piece and find a larger independent set. But then, can you piece them together to get a large independent set overall? That's not clear because there are going to be some edges that you cut between the pieces. And well, basically the conclusion is that it seems to us that decomposition by removing small fractional edges cannot work. So we thought a lot about how to do this. And one natural idea is to do vertex expander decomposition. So suppose you're able to find a non-vertex expanding subset in the graph, and then you can remove its neighbors. There are going to be few neighbors. You can remove them. Now the remaining two pieces are disconnected. So then you can recurse on them, and then in the end you can union the independent sets. This is the main reason that we have our third result, which we try very hard to replace the second eigenvalue bound by vertex expansion. But for vertex expansion, we don't have a natural sum of squares certificate. So this is why here we need to assume that. And the natural question is, can we decompose the graph in a way such that we get certified small-sided vertex expanders? This we don't know. And we also don't know whether we can remove this part or not. So there are a lot of questions about how do you decompose and how do you get certificates, sum of square certificates that we don't know. Okay, so that's the end of my talk. Thank you.